Hello there. Welcome to the Sleepy Science Style. Tonight, we're setting out on a gentle journey through space and time to visit our galaxy's closest neighbor, the Andromeda Galaxy. It's a place of immense beauty and almost unimaginable scale, a vast island of stars that has been dancing with our own Milky Way through the darkness for billions of years. You'll learn about the rivers of stars flowing through Andromeda's spiral arms, the ancient light that has traveled for 2.5 million years to reach your eyes, the trillions of suns that shimmer and pulse within that distant cosmic city. And if these quiet explorations help you relax, if they offer you a small moment of peace in a fast-moving world, you might consider gently tapping the like button and subscribing to the channel. It helps others find their way here as well. Now let's begin. Andromeda is coming closer, right now. As you rest, the Andromeda Galaxy is moving toward our Milky Way at about 110 kilometers per second. That's roughly 250,000 miles per hour, faster than anything you've ever experienced. Yet on the cosmic scale, it's a slow, patient approach. Like two dancers who've been circling each other for eons, finally beginning to move together for the embrace that was always inevitable. But you don't need to worry about this cosmic collision. It won't happen for another 4 billion years, give or take a few hundred million. For billion years. When these two galaxies finally meet, when their outer edges first touch and their gravity begins the long work of merging them into one, our sun will have already lived most of its life. The Earth will be a very different place, if it exists at all in any form we'd recognize. The collision itself will be gentle despite its immensity, like two clouds drifting together, interpenetrating, becoming something new. Stars won't crash into each other because the distances between stars are so vast, so impossibly empty. It will be a merger measured in millions of years, a slow cosmic dance captured in computer simulations that compress eons into minutes. For now, just rest knowing that some meetings are worth the wait, even if they take half the age of the universe to unfold. You can see Andromeda with your naked eyes on a clear, dark night. This is one of those facts that seems almost impossible. Something so distant that its light takes 2.5 million years to reach us. Visible without any tools or technology. Just your eyes and the darkness and the patience to look up. It appears as a faint, fuzzy patch in the constellation Andromeda, best viewed in autumn if you're in the northern hemisphere, away from city lights where the sky still remembers how to be truly dark. The light you see when you look at Andromeda left that galaxy before humans existed, before Homo sapiens walked the Earth, before our ancestors came down from the trees, when the African savanna was home to very different creatures than those who would one day build telescopes and write poetry about stars. That ancient light crossed the void, traveling through the infinite nothing, carrying information about trillion-year-old suns and stellar nurseries and cosmic processes we're only beginning to understand. And it arrives in your eye, this moment, connecting you to a place so far away that distance loses its meaning. The next time you're somewhere dark enough to see it, somewhere the light pollution hasn't stolen the stars, look for that faint smudge. Know that you're seeing deep time made visible. You're catching photons that began their journey before language, before art, before agriculture, before everything that makes us human. Some people say it's humbling. Others find it strangely comforting. Either way, it's there every clear night, whether you look or not. Andromeda contains approximately 1 trillion stars. 1 trillion. Let that number rest in your mind for a moment without trying to grasp it fully, because you can't. The human brain didn't evolve to comprehend trillion of anything. A trillion seconds is about 31,700 years. A trillion miles would take you far beyond our solar system, deep into interstellar space. $1 trillion stacked as $100 bills would reach halfway to the moon. And Andromeda has 1 trillion suns. Each of those stars is a furnace, fusing hydrogen into helium, generating energy through the same nuclear processes that power our own sun. Each one has its own story, its own age, its own future. Some are young and hot and blue, burning fiercely but briefly, like youth itself. Others, they're old and cool and red, patient giants that will shine for trillions of years more. Some are binary stars, dancing together in eternal orbit. Others might have planets, worlds we'll never see, orbiting suns we'll never name. Try to imagine just 1,000,000 of those stars, 1,000,000 points of light, each one a sun. Now multiply that by 1,000,000. That's Andromeda, a galaxy so vast it makes our galactic home seem modest despite the Milky Way's own 100 billion stars. And this is just one galaxy among hundreds of billions in the observable universe. The scale doesn't make sense, not really. And that's okay. Let it be too big. Let your mind rest against that incomprehensible magnitude the way you might rest against a mountain you'll never climb, secure in the knowledge that some things are meant to dwarf us. It puts our daily worries in perspective, doesn't it? That meeting you're nervous about, that argument you keep replaying, they matter to you, and they're real, but they're also tiny against the backdrop of 1,000,000,000,000 stars, and somehow that's comforting. The Andromeda Galaxy is about 220,000 light-years across. A light-year is the distance light travels in 1 year, moving at 186,000 miles per second, or about 5.8 trillion miles. So when we say Andromeda is 220,000 light-years across, we're saying it would take a beam of light 220,000 years to travel from one edge to the other. If you could somehow stand at one edge of Andromeda and shine a flashlight toward the other side, the light wouldn't reach the opposite shore until 220,000 years had passed. For comparison, our entire solar system, from the Sun to the edge of the Kuiper Belt where Pluto drifts, is about 5.5 light hours across. Just hours for light to traverse what seems infinite to us. The Milky Way is roughly 100,000 light-years in diameter, so Andromeda is more than twice as wide as our home galaxy. It's the larger sibling in this cosmic neighborhood, the big sister galaxy, though both are dwarfed by some of the giant elliptical galaxies that exist farther out in the universe, monsters that span millions of light years. But even describing these distances doesn't quite capture what they mean. Maybe it's enough to know that Andromeda is vast beyond imagining, a disk of stars and gas and mystery that would swallow our solar system without noticing. That makes the space between Earth and our moon seem like a crack in the sidewalk. We live in a universe that operates on scales our minds can't hold, and there's something peaceful about accepting that. You don't need to understand it. You can just let it be enormous and drift. Andromeda has a supermassive black hole at its center. Actually, it has two, which is unusual and intriguing. The larger one contains about 110 million solar masses, meaning it's 110 million times more massive than our Sun, all compressed into a point so dense that nothing, not even light, can escape once it crosses the event horizon. The smaller companion black hole is still being studied, still revealing its secrets to the astronomers who peer at that distant center with instruments that see in wavelengths our eyes never could. These black holes are thought to be the remnants of a galactic merger, evidence that Andromeda consumed another galaxy sometime in its past, swallowing it whole over millions of years, adding its stars and gas and darkness to itself. The two central black holes spiraled together but haven't yet merged, still orbiting each other in that crowded core, though eventually, inevitably, they'll join into one even more massive gravitational well. A black hole is a strange thing to contemplate while trying to sleep. A tear in space-time, a place where the universe's fabric is bent so sharply that it breaks, where time slows and space curves, and all our intuitions about how reality works simply fail. But there's something quietly fascinating about them too, something almost meditative. They're patient, they're inevitable. They follow the rules of physics perfectly, absolutely, without exception. They exist beyond our scales of good and bad, beyond human meaning, just being what they are. The universe's way of taking matter and energy and hiding it away in a pocket dimension we call a singularity. You're safe from these black holes. They're 2.5 million light years away, and even if they weren't, even if one existed in our solar system, you'd need to get very close before you'd be in danger. Space is so empty, so vast, that even its monsters have room to exist without threatening us. Rest easy. Andromeda's spiral arms are rivers of stars flowing through the dark. When you see images of Andromeda, those graceful curves of light that swirl out from the galactic center, you're seeing density waves, patterns where stars cluster more thickly as they orbit. The arms aren't solid structures, not really. They're more like traffic jams in the flow of stellar motion, places where the orbit of stars slows and crowds, creating bright lanes that persist even as individual stars drift in and out. Think of it like cars on a highway. Sometimes traffic bunches up, creating a slow-moving wall of vehicles even though there's no accident, no obstacle, just the mathematics of movement and density. Eventually you pass through the congestion and speed up again, but the traffic jam remains for the next wave of cars. That's similar to how spiral arms work. Stars move into the dense regions, slow down, light up the arm with their combined glow, then move out the other side, while new stars come in behind them. The pattern persists even as the participants constantly change. These arms are also stellar nurseries, places where giant molecular clouds collapse under their own gravity to form new stars. The dense regions trigger star formation, and those young, massive stars are bright and blue, living fast and dying young in supernova explosions that seed the arms with heavy elements and compress nearby gas clouds, triggering even more star formation. It's a cycle that feeds itself, a cosmic engine of creation that's been running for billions of years. From our perspective, those spiral arms are frozen, unchanging. We don't live long enough to see them evolve. Our recorded history is a tiny fraction of the time it takes for any noticeable change in galactic structure. But if you could watch Andromeda in time-lapse, speeding up billions of years into seconds, you'd see those arms swirl and shift and reform, a slow cosmic pinwheel turning in the dark. For now, though, they're still patient, eternal, on any timescale that matters to you. There are at least 25 smaller galaxies orbiting Andromeda. These are satellite galaxies, dwarf galaxies, tiny compared to their host, but each containing millions or billions of stars of their own. They orbit Andromeda the way moons orbit a planet, held by gravity, trapped in that massive gravitational well, but maintaining their own identity, their own structure, at least for now. The largest of these is M32, a compact elliptical galaxy that may have once been much larger before tidal forces from Andromeda stripped away its outer stars and gas, leaving behind a dense core. There's also M110, a dwarf elliptical with its own population of aging stars and dark matter. These companions are visible in telescopes as small fuzzy patches near the much brighter disk of Andromeda. Easy to overlook, but fascinating in their own right. Over time, many of these satellite galaxies will be cannibalized by Andromeda, torn apart by tidal forces, their stars scattered into the larger galaxy's halo or added to its disk. This is how galaxies grow, through galactic cannibalism, by consuming their smaller neighbors. It sounds violent, but it's a slow process, gentle by cosmic standards, taking hundreds of millions of years. By the time it's complete, the stars that once belonged to the dwarf galaxy are simply part of Andromeda, indistinguishable from all the others, their original identity erased by time and gravity. Our Milky Way has its own satellite galaxies too, including the large and small Magellanic Clouds visible from the southern hemisphere. We're doing the same thing Andromeda does, slowly pulling in our neighbors, growing through gravitational capture. It's the way of galaxies, this slow accretion, this patient consumption. And when Andromeda and the Milky Way finally merge, all these satellite galaxies will merge too, creating one enormous elliptical galaxy that some astronomers have already nicknamed Milkomeda. But that's billions of years away. For now, these smaller galaxies still dance around their hosts, still maintain their independence, like children who haven't quite left home. The Andromeda Galaxy was first recorded by the Persian astronomer Abd al-Rahman al-Sufi in 964 AD. In his book of Fixed Stars, he described it as a small cloud, a nebulous patch visible to the naked eye in the constellation Andromeda. He didn't know it was a galaxy, of course. No one did until the 20th century. For nearly 1,000 years, Andromeda was simply a curious fuzzy spot, catalogued and observed but not understood. In 1612, German astronomer Simon Marius observed it through a telescope and described it as looking like a candle flame seen through horn, that cloudy, translucent material used in lanterns before glass became common. He still didn't know what it was. Neither did anyone else for centuries. It was listed in Charles Messier's famous catalog as M31, the 31st object in his list of things that weren't comets, things that might confuse comet hunters with their fuzzy appearance. The breakthrough came in the 1920s when Edwin Hubble used the 100-inch telescope at Mount Wilson Observatory to resolve individual stars in Andromeda. Among those stars, he found Cepheid variables, special stars whose brightness pulses in a regular period that's related to their intrinsic luminosity. By measuring the period and apparent brightness of these Cepheids, Hubble could calculate their distance, and the result was shocking. Andromeda was far outside the Milky Way, nearly 1 million light-years away by his calculations, though we now know it's about 2.5 million light-years distant. This discovery revolutionized our understanding of the universe. Suddenly, the cosmos was vastly larger than anyone had imagined. The Milky Way wasn't the entire universe, but just one galaxy among many, an island in an ocean of space. Andromeda was proof of other galaxies, other cosmic cities of stars, and once astronomers knew what to look for, they found galaxies everywhere they pointed their telescopes. Billions of them, scattered through space as far as we can see. It's humbling to think that for most of human history, we didn't know galaxies existed. We couldn't see the scope of creation, couldn't grasp our place in the cosmic hierarchy. Now we know, and the knowledge is both overwhelming and oddly peaceful. We're smaller than we thought, but we're part of something much larger, something ancient and vast and beautiful. Andromeda contains about twice as much dark matter as visible matter. Dark matter is one of the great mysteries of modern cosmology, an invisible substance that doesn't emit, absorb, or reflect light, detectable only by its gravitational effects. We know it's there because galaxies rotate in ways that visible matter alone can't explain. The stars in the outer regions of galaxies move faster than they should if only the mass we can see is present. There must be something else, something dark, providing additional gravity. In Andromeda, this dark matter forms an enormous halo that extends far beyond the visible disk of stars. It's a ghostly sphere of mass surrounding the bright galaxy, invisible but present, holding everything together with its gravity. Without this dark matter, the galaxy would likely fly apart, the stars in the outer regions spinning off into intergalactic space. Dark matter is the scaffolding upon which visible galaxies are built, the foundation that allows galactic structure to exist. We don't know what dark matter is made of. It's not atoms or normal matter. It might be exotic particles that barely interact with ordinary matter except through gravity. It might be something we haven't even imagined yet. Experiments deep underground and in space are searching for it, trying to detect individual dark matter particles. But so far it remains elusive. It's one of the biggest unsolved problems in physics, a mystery that spans the universe. There's something almost poetic about it, isn't there? The idea that most of the universe is made of something we can't see, something invisible and mysterious that holds galaxies together. It reminds us how much we don't know, how much remains to be discovered. Even as our knowledge grows, the universe keeps revealing new mysteries, new questions, new frontiers. And that's okay. That's how it should be. Mystery is part of the beauty, not knowing everything. Being humble before the vastness of creation, having questions that might take centuries to answer or might never be answered at all. There's peace in accepting that some things are meant to remain mysterious, at least for now. The halo of Andromeda extends about 2 million light-years from the galaxy's center. This is the extent of its gravitational influence, the region where Andromeda's dark matter halo dominates. where its gravity is the strongest force shaping the motion of nearby objects. Within this halo sit those satellite dwarf galaxies, orbiting their massive host, and at the outer edges, the halo actually overlaps with the Milky Way's own halo. The merger of Andromeda and the Milky Way has already begun, at least in these outermost regions. The collision that won't fully unfold for 4 billion years has, in its earliest stages, already started. This halo contains hot gas as well as dark matter, a plasma heated to millions of degrees by the galaxy's gravity and the energy from dying stars. This gas is so hot it shines in X-rays, invisible to optical telescopes, but bright in the X-ray spectrum. The halo is a reservoir of material that can feed future star formation, gas that will gradually fall into the galactic disk, cooling and condensing into new molecular clouds, new stars, new generations of stellar life. Imagine it, an enormous sphere of mostly invisible matter and superheated gas, extending millions of light years, dwarfing the visible galaxy at its heart. That's the true size of Andromeda, the full extent of its presence in space. What we see with our eyes, or even with optical telescopes, is just the bright core, the tip of the iceberg, a small fraction of the galaxy's total mass and volume. Most of Andromeda is dark and hot and hidden, revealed only by gravitational effects and X-ray observations. It's a reminder that what we see is often just the surface of something much deeper. Andromeda has about 450 globular clusters. These are tight spherical collections of ancient stars, some of the oldest stars in the galaxy, formed when Andromeda was young. Each globular cluster contains tens of thousands to hundreds of thousands of stars packed, so closely together that near their centers, stars might be separated by just light weeks or light days rather than the light years that separate stars in the galactic disk. These clusters orbit Andromeda in elongated elliptical paths, their orbits taking them far above and below the galactic plane, out into the halo and back again in cycles that last hundreds of millions of years. They're like bees around a hive or satellites around a planet, bound by gravity but following their own trajectories, independent and ancient. The stars and globular clusters are metal-poor, meaning they contain very few elements heavier than hydrogen and helium. This is characteristic of old stars, stars that formed before multiple generations of supernovae had enriched the interstellar medium with the heavy elements that make up planets and people. These are first-generation stars, or close to it, relics of the early universe when galaxies were young and the periodic table was simpler. Studying Andromeda's globular clusters gives astronomers clues about the galaxy's formation and history. The distribution and properties of these clusters tell a story of mergers and star formation, of the conditions that existed billions of years ago when the galaxy was assembling itself from smaller pieces. Some of the clusters were likely born within Andromeda. Others probably came from dwarf galaxies that were later consumed, remnants of structures that no longer exist as separate entities. If you could somehow visit a globular cluster, the night sky would be spectacular. Thousands of stars would be visible to the naked eye, bright enough to read by, turning night into a strange twilight. There would be no darkness, just a sky ablaze with ancient suns. But we're far from these clusters, observing them from a safe distance as points of light in the halo of a distant galaxy. They're beyond our reach, but not beyond our ability to study and wonder. Star formation in Andromeda is less active than in the Milky Way. Our home galaxy produces about 1 to 2 new stars per year on average. Andromeda, despite being larger, forms stars at only about half that rate. This is because Andromeda has less gas available for star formation, having converted more of its supply into stars over its long history, and also because its last major merger was longer ago, meaning it's had more time to settle down. Galaxies go through phases. After a major merger, star formation can spike dramatically as gas clouds collide and compress, triggering a burst of new stellar births. Then, over time, the star formation rate declines as the available gas is used up and the galaxy settles into a more quiescent state. Andromeda is currently in a relatively quiet phase, still forming stars, but not at the frenetic pace of a starburst galaxy. The star formation that does occur tends to happen in the spiral arms, in those dense regions where gas clouds are most likely to collapse. There are stellar nurseries in Andromeda, massive molecular clouds where dozens or hundreds of stars are being born right now, cocoons of gas and dust hiding the violent processes within. In a few million years, those clouds will be blown away by the radiation and stellar winds from the young stars they created, revealing open clusters of newborn suns. This slower pace of star formation means Andromeda is, in some sense, aging more gracefully than the Milky Way. It's used its resources more efficiently, or at least more completely. Eventually, all galaxies will run out of gas for star formation, transitioning from blue, active spirals to red, quiescent ellipticals as their stellar populations age. Andromeda is farther along this path than we are, though both galaxies still have billions of years of star formation ahead of them before their reserves are truly exhausted. In a way, galaxies are like living things, born from the coalescence of dark matter and gas in the early universe, growing through accretion and mergers, going through active and quiet phases, eventually aging into senescence when their fuel for star formation is depleted. Andromeda is middle-aged, mature, past the wild youth of rapid star formation, but not yet old, not yet running out of energy and light. It's a galaxy in its prime, and we're fortunate to be able to observe it so clearly from our cosmic neighborhood. The oldest stars in Andromeda are approximately 13 billion years old. That's nearly as old as the universe itself, which is about 13.8 billion years old. These ancient stars formed when the universe was young, when the first galaxies were condensing out of the primordial gas that filled space after the Big Bang. They've been shining since before the Earth existed, before the Sun formed, before anything in our solar system had even begun to take shape. These old stars are cool and red, having burned through much of their nuclear fuel, but not massive enough to have exploded as supernova. They're patient stars, conservative with their energy, existing in a state of slow decline that will last for trillions of years more. Some of them might be the last stars to die in the universe, long after most other stars have burned out, long after galaxies have stopped forming new stars, flickering alone in the darkness of a cold, expanded cosmos. When you look at Andromeda, some of the photons entering your eye were emitted by these ancient stars. You're seeing light from objects that were already old when our planet was young, already ancient when the first life stirred in Earth's oceans. These stars have witnessed the entire history of our solar system from afar, indifferent observers across an unbridgeable gulf of space. They've seen the formation of our sun, the coalescence of the planets, the rise and fall of countless species on our world, all without ever knowing we exist, without ever being affected by our presence. There's something deeply humbling about that. We think of ourselves as important, as central to the story, but from the perspective of those ancient stars, we're not even a footnote. We're a fleeting moment in cosmic time, a brief spark in the darkness. And yet, we're here. We're conscious. We're looking back at those stars and thinking about them, measuring them, understanding them. In some small way, the universe has become aware of itself through us. And that's remarkable. That's worth celebrating, even as we drift towards sleep. Andromeda's disk is warped. If you could see the galaxy edge on, you'd notice that the plane of stars and gas isn't perfectly flat, but twisted, rippling like a sheet caught in a breeze. This warping is caused by gravitational interactions with nearby galaxies, tidal forces pulling on the disk, distorting it over millions of years. The satellite galaxies orbiting Andromeda tug at its structure, and Andromeda tugs back, creating these graceful curves and ripples in what would otherwise be a flat disk. Our own Milky Way is warped too, for similar reasons. In fact, most large spiral galaxies show some degree of warping when you look closely enough. It's a sign that galaxies don't exist in isolation, but are constantly being shaped by their environment, by the gravitational influences of neighbors near and far. Every galaxy is in conversation with its surroundings, responding to forces that act over cosmic distances and timescales. Studying these warps helps astronomers understand the distribution of dark matter in and around galaxies. The way a disk bends and twists depends on the mass pulling on it, and since most of that mass is dark matter, the warp becomes a tool for mapping the invisible. It's like watching a bedsheet settle over furniture in a dark room. You can't see the furniture directly, but you can see its shape revealed by the fabric draped over it. Andromeda's warp is subtle, gentle, barely noticeable except in careful measurements and detailed images. But it's there, a testament to the gravitational ballet that galaxies perform, pulling and pushing on each other across the void. Even structures as vast as galaxies are subject to influence, are shaped by relationship and proximity. Nothing in the universe exists entirely alone. There are stars in intergalactic space between the Milky Way and Andromeda. These are rogue stars, ejected from their home galaxies by gravitational interactions or supernova explosions, now drifting alone through the void between galactic islands. They have no galaxy to call home, no spiral arm to orbit, just empty space stretching in all directions for millions of light years. Some of these stars were likely thrown out during past encounters between Andromeda and its satellite galaxies, or when dwarf galaxies were torn apart by tidal forces. Others might have been ejected by close encounters with the supermassive black holes at galactic centers, flung outward at high speed like stones from a slingshot. Once they're in intergalactic space, there's usually nothing to bring them back. They'll drift for billions of years, lone wanderers in the darkness. If there are planets around these intergalactic stars, if there's life on those planets, what would the night sky look like? Without a galaxy surrounding them, without the milky band of the galactic disk overhead, the sky would be dominated by two large fuzzy patches. The Milky Way in one direction, Andromeda in another, both seen from outside, both visible as complete spiral structures. It would be a sky of profound darkness punctuated by those two bright islands, a view no one from within a galaxy could ever have. These intergalactic stars are difficult to detect because they're so far from the bright backgrounds of galaxies, but astronomers have found some of them, traced their motions, calculated their origins. They're reminders that the space between galaxies isn't completely empty, that cosmic accidents and gravitational violence can send objects flying into the void, creating new populations in places where stars shouldn't exist. The universe is messy, chaotic, full of exceptions and outliers. And that's part of its beauty. The light from Andromeda that reaches Earth tonight is redshifted, but not because of universal expansion. Normally, distant galaxies appear redshifted, their light stretched toward longer, redder wavelengths by the expansion of space itself. The farther away a galaxy is, the faster space expands between us and it, and the more its light is redshifted. This is how we know the universe is expanding, how we discovered that cosmic expansion in the first place. But Andromeda is special. Despite being 2.5 million light years away, it's not receding from us. It's approaching. The light from Andromeda is actually blue shifted, compressed to shorter wavelengths by the Doppler effect, because the galaxy is moving toward us at 110 kilometers per second. This approach velocity is strong enough to overcome the expansion of space at this local scale. Gravity wins here, pulling Andromeda and the Milky Way together despite the universe's overall expansion. This makes Andromeda one of the few galaxies in the observable universe that's blue-shifted. Almost everything else is red-shifted, fleeing from us as space expands. But our local group of galaxies, the Milky Way, Andromeda, and the smaller galaxies bound to both, are gravitationally tied together, moving as a unit, eventually to merge into a single structure. We're not expanding away from each other. We're falling together, slowly, inevitably, like dancers moving to music we can't hear. In a way, this is comforting. Amid the universal expansion that will eventually stretch the cosmos until galaxies are isolated islands in an ever-growing void, unable to see each other across the expanding darkness, our local group will stay together. We'll merge and mix and become something new, but we won't drift apart into infinite loneliness. At least not for trillions of years. Not until the universe is old and cold and the last stars are dying. For now, on cosmic scales, we have each other. Andromeda's spiral structure may have been shaped by a collision with another galaxy about 2 billion years ago. Evidence for this comes from computer simulations that try to reproduce Andromeda's current structure and the distribution of stars in its disk. The simulations suggest that a smaller galaxy, perhaps about 20% of Andromeda's mass, plunged through Andromeda's disk sometime in the relatively recent past, cosmically speaking. This collision would have sent ripples through the disk, density waves that compressed gas and triggered bursts of star formation. It would have heated the disk, puffing it up, adding velocity to stars and scrambling their orbits. Over time, the smaller galaxy was destroyed, its stars scattered throughout Andromeda, its identity erased. But the effects of that collision persist, visible in the structure of the disk, in the orbits of stars, in the patterns that astronomers measure and try to decode. Galactic collisions sound violent, and in terms of energy they are. The kinetic energy involved is enormous. But from an individual star's perspective, collisions are almost gentle. Stars are so far apart that even when two galaxies merge, individual stars almost never collide. They pass by each other like ghosts, like two schools of fish interpenetrating without individual fish ever touching. It's the gravitational effects that matter, the tidal forces, the way orbits are scrambled and gas clouds are compressed. In about 4 billion years, when Andromeda and the Milky Way collide, it will be a similar process. Over a few 100 million years, the two galaxies will merge, and during that time our Sun will pass through the disk of Andromeda, and Andromedan stars will pass through our disk, but the Sun will almost certainly never have a close encounter with another star. Space is just too empty, the gap's too vast. The collision will reshape both galaxies, but on a stellar level, it will be surprisingly peaceful. Andromeda rotates, spinning like a cosmic pinwheel, but different parts rotate at different speeds. Near the center, stars complete an orbit in just a few tens of millions of years, whipping around the galactic core at high velocity. Farther out, in the spiral arms where most of the visible stars reside, orbital periods stretch to a few 100 million years. At the very edges, in the sparse outer disk, a single orbit might take 500 million years or more. This differential rotation is what creates and maintains the spiral structure. If the galaxy rotated like a solid disk, with all parts moving at the same angular velocity, the spiral arms would wind up tighter and tighter until they disappeared. But because the inner parts rotate faster, the arms are constantly being sheared, stretched, reformed. Density waves move through the disk at a different speed than the stars themselves, creating the persistent pattern we observe. Our own Sun orbits the Milky Way once every 225 to 250 million years, a period sometimes called a cosmic year or galactic year. The Sun is about 20 galactic years old, having completed about 20 orbits around the galactic center since it formed. When the Sun completes its next orbit, Earth will have been around the galaxy 21 times. By then, if humanity still exists, we'll have witnessed changes and events we can't imagine, but the galaxy will look much the same, the spiral arms in roughly the same positions, turning slowly in the darkness. It's grounding, in a way, to think about these vast cycles. The Sun's orbit taking longer than the entire history of complex life on Earth. Andromeda's rotation, so slow that civilizations rise and fall in the blink, contained, manageable. Sometimes it helps to remember that the galaxy doesn't notice our stress, doesn't care about our deadlines. It just keeps turning, patient and eternal. There are planetary nebulae scattered throughout Andromeda. These are the glowing shells of gas ejected by dying stars, stars that were once similar to our Sun, but have exhausted their nuclear fuel and shed their outer layers into space. The remnant stellar core, now a white dwarf, illuminates this expanding shell with ultraviolet radiation, causing it to glow in beautiful colors: reds, greens, blues, like cosmic Christmas ornaments scattered through the galaxy. Each planetary nebula is the final artwork of a star's life, a brief phase lasting only tens of thousands of years before the gas disperses and fades. During this time, the nebula expands, the shell growing larger and thinner, the colors shifting as different elements are ionized by the central star's radiation. Eventually, the white dwarf cools and dims, and the nebula becomes too diffuse to see, its material mixing back into the interstellar medium to be recycled into future generations of stars. In Andromeda, there are thousands of these nebulae, each one marking the death of a sun-like star. They're too small and faint to see individually from Earth, but astronomers have detected them through spectroscopy and careful observation. Each one represents a star that lived for billions of years, fusing hydrogen in its core, perhaps hosting planets, perhaps illuminating worlds where life arose. And now it's over, the star reduced to a cooling cinder, its outer layers expanded into space, contributing carbon and nitrogen and oxygen to the interstellar medium. Our sun will end this way too, in about 5 billion years. It will swell into a red giant, swallowing Mercury and Venus, perhaps reaching out to touch Earth. Then it will eject its outer layers, creating its own planetary nebula, a final display of light before settling into white dwarf status. The nebula will expand and fade, and the sun will cool over trillions of years, eventually becoming a black dwarf, a stellar remnant that no longer shines. But that's so far in the future it's almost meaningless to us now. For now, the sun is stable, reliable, warming Earth, nurturing life, and it will be for billions of years more. Andromeda's mass is estimated at about 1.5 trillion solar masses. That's the combined mass of all its stars, all its gas, and all its dark matter. About 200 billion solar masses of that is in stars, the visible mass, the trillion suns we talked about earlier. The rest is mostly dark matter, along with some gas and dust. This mass is what creates Andromeda's gravitational pull, what holds the galaxy together, and what will eventually pull it into collision with the Milky Way. The Milky Way's mass is harder to measure since we're inside it, but current estimates put it around 1 trillion solar masses, making Andromeda somewhat more massive. This matters for the eventual merger. When two galaxies collide, the more massive one tends to dominate the final structure. So when Andromeda and the Milky Way merge, the resulting galaxy will be more Andromeda than Milky Way, at least in terms of mass contribution. But both will be so thoroughly mixed that the distinction will be meaningless. Measuring galactic masses is tricky. You can't just count the stars and add them up because most of the mass is dark matter, which doesn't shine. Instead, astronomers measure the velocities of stars and gas at various distances from the galactic center. Using the laws of physics, specifically Newton's laws of motion and gravity, they can calculate how much mass must be present to keep those stars in their observed orbits. It's an indirect method, but it works, giving us surprisingly accurate estimates of galactic masses. This technique revealed the existence of dark matter in the first place. When Vera Rubin and Kent Ford measured the rotation curves of galaxies in the 1970s, they found that stars in the outer regions were moving much faster than expected. According to their visible mass, these stars should have been moving more slowly, or they should have flown off into intergalactic space. The fact that they stayed in orbit meant there was more mass present than they could see. Dark matter was the solution, an invisible mass that provided the extra gravity needed to explain the observations. Andromeda was part of this story, one of the galaxies whose rotation curve helped establish the existence of dark matter. Its mass, measured by the motions of its stars, exceeded the mass of visible matter by a factor of 5 or 6. That discrepancy, confirmed in galaxy after galaxy, revolutionized cosmology and physics. Now we know that dark matter makes up about 85% of the matter in the universe, with ordinary matter, the stuff of stars and planets and people, making up only about 15%. We're the minority, built from the rare material, surrounded by an invisible ocean of something else. Blue stars in Andromeda are young, hot, and destined to die quickly. These massive stars, 10 or 20 or 50 times the mass of the Sun, burn their nuclear fuel prodigiously, shining with intense brightness, but living only a few million to a few tens of millions of years. In galactic terms, that's a blink, barely a moment. They're born in stellar nurseries, formed from collapsing gas clouds, and they die in spectacular supernova explosions, seeding the galaxy with heavy elements, and sometimes leaving behind neutron stars or black holes. These blue stars are found primarily in the spiral arms of Andromeda, in regions of active star formation where gas clouds are being compressed by density waves and triggered into collapse. They're beacons of youth, markers of recent star formation, their blue light dominating the spectrum of the spiral arms. When you see images of Andromeda, those bright blue knots along the arms are clusters of these young, massive stars, illuminating the gas clouds from which they formed. Because they live fast and die young, blue stars are a kind of clock. If you see a population of blue stars in a galaxy, you know star formation happened there relatively recently, within the last few tens of millions of years. If a galaxy has no blue stars, it means star formation ceased long ago, and all the massive stars have already died. This helps astronomers understand the history of galaxies, when they were actively forming stars, and when they entered quiescent phases. In a way, these massive blue stars are the rock stars of the galaxy, burning bright, but flaming out quickly, leaving dramatic corpses behind. They're not like our Sun, which is middle-aged and will live for billions of years more, slowly and steadily converting hydrogen to helium. Blue stars are intense, profligate with their energy, living for now without thought to tomorrow. And when they die, they do so violently, in explosions that briefly outshine entire galaxies, sending shockwaves through the interstellar medium that will trigger new generations of star formation. Even in death, they contribute to the life cycle of the galaxy. Red stars in Andromeda are old, cool, and patient. These are stars with less mass than the Sun, or stars that have evolved off the main sequence into red giants. Stars that have left their hydrogen-burning youth behind and entered a more sedate phase of existence. They shine with a reddish light, cooler than our Sun, often pulsing or varying in brightness as their outer layers expand and contract. The most common stars in any galaxy are red dwarfs, tiny stars with just a fraction of the Sun's mass, burning hydrogen so slowly that they'll live for trillions of years. These stars are so faint that none of them are visible to the naked eye from Earth, even in our own galaxy. But they make up about 70% of all stars, a vast population of dim, long-lived objects that will be the last stars shining when the universe is old. Red giants are different. These are evolved stars, stars that have exhausted the hydrogen in their cores and begun fusing helium or heavier elements. Their cores contract and heat up while their outer layers expand and cool, creating these bloated, reddish stars that can be hundreds of times larger than they were in their youth. Betelgeuse in our own sky is a famous red supergiant, a massive star near the end of its life. Andromeda has countless red giants, each one a sun nearing the end of its days. When you look at an image of Andromeda, the reddish color of the central bulge comes from these old red stars. The bulge is populated mostly by ancient stellar populations, stars that formed billions of years ago and have now evolved into red giants or low-mass stars that were always red. It's a sign of age, of maturity, of a galaxy that has been around for a long time and has used up much of its gas for star formation. The blue arms are where youth resides. The red center is where age and wisdom dwell. There's a human parallel here, isn't there? We start bright and energetic, burning hot, living fast. And as we age, we cool, we slow down, we become more patient and steady. We might not shine as brightly, but we last longer, we endure. The galaxy embodies the same cycle, and there's something comforting in that. Age isn't the end. It's another phase, another way of being with its own kind of beauty. Andromeda has experienced multiple major mergers in its history. The evidence is written in its structure, the unusual distribution of stars in the halo, the presence of streams and shells of stars that don't belong to the main disk, the two supermassive black holes at its center. Each of these is a clue, a fossil record of past violence and assimilation. Galaxies grow through mergers. Small galaxies merge to form larger ones, and those merge with others, a hierarchical process that's been ongoing since the first galaxies formed about 13 billion years ago. Andromeda is the result of many such mergers, each one adding mass and stars and complexity to the growing structure. Some mergers were major, bringing in substantial mass and dramatically altering the galaxy's structure. Others were minor, small dwarf galaxies that were consumed without much fanfare, their stars absorbed into the halo. This process continues today. Andromeda is still consuming its satellite galaxies, still growing, still evolving. And in 4 billion years, it will undergo its most significant merger yet when it collides with the Milky Way. That merger will be roughly equal, two large spiral galaxies coming together, creating something new. The resulting galaxy will likely be an elliptical, a football-shaped collection of stars with no spiral structure, just a smooth distribution of stellar orbits. The spiral arms will be destroyed in the merger, the disks disrupted, the stars scattered into new configurations. From the perspective of individual stars, this is fine. They'll survive, they'll keep shining, just in new orbits around a new galactic center. From the perspective of the overall structure, it's transformative. Two beautiful spirals will be gone, replaced by a single elliptical. But that elliptical will be beautiful too, in its own way, a testament to the union of two great galactic civilizations. It will be called Milkomeda, or perhaps something else by then, and it will drift through space, a merged entity, waiting for whatever comes next in the life of the universe. Andromeda's stellar halo contains ancient streams and shells. These are structures created by tidal disruption of satellite galaxies, long trails of stars stretching through space, marking the paths where smaller galaxies were torn apart by Andromeda's gravity. Some of these streams are millions of light years long, vast structures visible only because they contain stars that betray their presence through their motion and position. Astronomers study these streams to understand Andromeda's merger history and the distribution of dark matter in its halo. The shape and motion of a tidal stream depends on the gravitational field it's moving through. So by mapping the streams and comparing them to simulations, researchers can infer the structure of the halo, including how the dark matter is distributed. It's like forensic astronomy, reading the clues left behind by ancient events to reconstruct what happened. Some streams are relatively young, their stars still clustered, their paths still clear. Others are old and dispersed, stretched and mixed until they're barely distinguishable from the general halo population. Each one tells a story of a galaxy that no longer exists, a structure that was destroyed and assimilated, leaving only these ghostly trails as evidence of its former existence. Our own Milky Way has similar streams. The most famous is the Sagittarius Stream, created by the ongoing destruction of the Sagittarius dwarf elliptical galaxy, which is currently being torn apart by our galaxy's tidal forces. The stream wraps completely around the Milky Way, a river of stars from a dying galaxy. Someday, Sagittarius will be completely gone, its stars fully mixed into our galaxy, and only the stream will remain as a memory of what it once was. These streams are melancholy, in a way. They're evidence of destruction, of galaxies that were once whole and are now scattered. But they're also evidence of creation, of how larger structures grow through the consumption of smaller ones. It's the way of the universe, birth through destruction, growth through consumption. New things are rising from the ruins of the old. Nothing lasts forever, not even galaxies. But their matter persists, transformed, incorporated into something new. Cepheid variable stars in Andromeda pulse with regular periods. These are special stars, evolved giants that have swollen to large size and become unstable, their outer layers expanding and contracting in a regular rhythm. The period of pulsation, how long it takes for the star to brighten and dim and brighten again, is directly related to the star's intrinsic luminosity. Brighter Cepheids pulse more slowly, dimmer ones pulse faster. This relationship makes Cepheids invaluable for measuring cosmic distances. If you can identify a Cepheid and measure its period, you know its true brightness. By comparing that to how bright it appears from Earth, you can calculate how far away it is using the inverse square law of light. This is how Edwin Hubble measured the distance to Andromeda in the 1920s, proving it was far outside the Milky Way and establishing the existence of other galaxies. The Cepheids in Andromeda pulse over days or weeks. Some have periods of a few days, others of tens of days. Each one is a cosmic lighthouse, flashing with a period that encodes its distance, waiting for astronomers to decode the message. Modern observations with the Hubble Space Telescope and other instruments have identified thousands of Cepheids in Andromeda, refining our distance measurements to about 2.54 million light-years with remarkable precision. These pulsing stars are red and yellow giants, evolved stars that have left the main sequence and entered this unstable phase. They won't pulse forever. Eventually they'll settle down or evolve further, becoming white dwarfs or exploding as supernovae, depending on their mass. But for now, they pulse, and their pulsation is useful, helping us map the universe and understand the cosmic distance scale. There's something almost musical about Cepheid variables, isn't there? Stars that breathe, expanding and contracting like lungs, brightening and dimming like a slow heartbeat. If you could hear them, maybe they'd sound like a cosmic drum, each star keeping its own tempo, together creating a symphony of pulsation across the galaxy. Of course, space is a vacuum and sound doesn't travel there, but the metaphor is lovely. The galaxy hums with periodic motions, with cycles and rhythms, with patterns that repeat over days and months and millions of years. In about 4 billion years, our solar system will likely be ejected into intergalactic space during the Milky Way Andromeda merger. Computer simulations of the collision show that while many stars will end up in the merged galaxy's central regions, a significant fraction, perhaps 10–20%, will be flung outward by gravitational interactions, sent flying into the space between what were once separate galaxies. If this happens to our solar system, it won't be catastrophic. The sun will keep shining, the planets will keep orbiting. We'll simply find ourselves in a different environment, no longer embedded in a galactic disk, no longer surrounded by the light of neighboring stars. The night sky, if anyone is around to see it, will be dramatically different. Instead of the Milky Way's band of light arching overhead, there will be a view of the merged galaxy from outside, a spectacular sight, but also a lonely one. The day-to-day effects on Earth, if it still exists, the sun will be nearing the red giant phase by then, will be minimal. The sun will still provide heat and light. The planets will still orbit, but the cosmic environment will have changed. We'll be intergalactic, exiles from our home galaxy, drifting through the vast emptiness between galactic islands. Eventually, universal expansion will push the nearest galaxies farther and farther away, until we're alone in our small corner of an expanding universe. Of course, this is so far in the future that it's almost abstract. 4 billion years is longer than Earth has existed. Life might not even survive that long on our planet. We might have long since spread to other worlds, or evolved into something unrecognizable, or gone extinct, leaving no trace. The merger will happen, but what it means for us is impossible to predict. Still, it's fascinating to think about, to imagine our solar system thrown into intergalactic space, watching the merger from a privileged vantage point, alone but safe, isolated but intact. Andromeda appears 6 times wider than the full moon when observed in long exposure images. This is one of those facts that surprises people. We think of the moon as large in our sky, dominating the night when it's full, impossible to miss. But Andromeda, despite being 2.5 million light-years away, actually covers a larger area of the sky. It's just so faint that most of it is invisible to the naked eye. When you look at Andromeda with unaided vision, you see only the bright central core, a small fuzzy patch. But in long-exposure photographs that capture the faint outer regions, the galaxy extends much farther, its full size revealed. The spiral arms, the outer halo, the vast extent of stars and gas, all of it larger in angular size than the moon. If our eyes were sensitive enough to see all of Andromeda's light, it would be a spectacular sight, dominating the constellation it resides in. This is a reminder that the universe is full of things we can't see, not because they're not there, but because our senses have limits. Telescopes and cameras extend those limits, revealing structure and beauty that would otherwise be invisible. How much else is out there, waiting to be seen by instruments we haven't invented yet? How much of reality are we missing because we lack the tools or the sensitivity to detect it? Andromeda is there every clear night, stretching across degrees of sky, a massive presence invisible to most observers. It's humbling, in a way. We walk around thinking we see the world as it is, but we're only seeing a tiny fraction, a narrow band of reality filtered through our limited senses. There's so much more, so much hidden in a plain sight, waiting for us to develop the eyes to see it. The name Andromeda comes from Greek mythology. Andromeda was a princess, daughter of King Cepheus and Queen Cassiopeia, who was chained to a rock as a sacrifice to appease Poseidon. She was rescued by the hero Perseus, who slew the sea monster Cetus and freed her. In the sky, these figures are all represented. Andromeda, Perseus, Cepheus, Cassiopeia, and Cetus, all positioned near each other in the northern sky, telling their ancient story across the constellations. The galaxy was named for the constellation it resides in, continuing a tradition of naming celestial objects after their positions in classical constellations. But there's something fitting about naming this galaxy after a princess who was saved, who survived her ordeal and went on to live a full life. Andromeda, the galaxy, will also survive, will merge with the Milky Way and be transformed but not destroyed, will become part of something new. Ancient cultures around the world told stories about the stars, creating meaning from patterns, connecting dots into figures and narratives. These stories helped people remember the sky, navigate by the stars, mark the seasons. They were mnemonic devices, but also art, ways of finding human significance in the inhuman vastness of space. We still use many of these ancient names and stories, still divide the sky according to boundaries drawn by Greek and Roman astronomers, still point to patches of light and call them by names that are thousands of years old. In some distant future, after the merger, what will we call the new galaxy? Milkomeda is the current favorite among astronomers, a portmanteau of Milky Way and Andromeda. But that's informal, playful. Will there be humans around to name it? Will they even care about such things? Will the galaxy be home to any life at all? Or will it be a lonely city of stars, unpopulated, shining for no one? The name Andromeda comes from Greek mythology. Andromeda was a princess, daughter of King Cepheus and Queen Cassiopeia, who was chained to a rock as a sacrifice to appease Poseidon. She was rescued by the hero Perseus, who slew the sea monster Cetus and freed her. In the sky, these figures are all represented. Andromeda, Perseus, Cepheus, Cassiopeia, and Cetus, all positioned near each other in the northern sky, telling their ancient story across the constellations. The galaxy was named for the constellation it resides in, continuing a tradition of naming celestial objects after their positions in classical constellations. But there's something fitting about naming this galaxy after a princess who was saved, who survived her ordeal and went on to live a full life. Andromeda, the galaxy, will also survive, will merge with the Milky Way and be transformed but not destroyed, will become part of something new. Ancient cultures around the world told stories about the stars, creating meaning from patterns, connecting dots into figures and narratives. These stories helped people remember the sky, navigate by the stars, mark the seasons. They were mnemonic devices, but also art, ways of finding human significance in the inhuman vastness of space. We still use many of these ancient names and stories, still divide the sky according to boundaries drawn by Greek and Roman astronomers, still point to patches of light and call them by names that are thousands of years old. In some distant future, after the merger, what will we call the new galaxy? Milkomeda is the current favorite among astronomers, a portmanteau of Milky Way and Andromeda, but that's informal, playful. Will there be humans around to name it? Will they even care about such things? Will the galaxy be home to any life at all? Or will it be a lonely city of stars, unpopulated, shining for no one? These are unanswerable questions, pleasant to ponder as you drift towards sleep. The future is unwritten, the story incomplete. For now, we have Andromeda, our neighbor, our future partner in cosmic dance, shining in the night sky, waiting. The space between stars and Andromeda is vast and empty. When we talk about 1 trillion stars in the galaxy, it sounds crowded, packed, but the reality is that space dominates. The average distance between stars in the galactic disk is about 5 light-years, roughly the distance from our Sun to Proxima Centauri, the nearest star to us. 5 light-years is almost incomprehensibly far, about 30 trillion miles. At that scale, even 1 trillion stars can fit comfortably with immense voids between them. This emptiness is why galactic collisions don't result in stellar collisions. When Andromeda and the Milky Way merge, the chances of any 2 stars actually hitting each other are astronomically small, almost zero. They'll pass by like ghosts, like 2 clouds of gnats interpenetrating without the individual insects colliding. The gravitational effects will be profound, scrambling orbits and reshaping the overall structure. But on a star-by-star level, it will be peaceful, almost non-event. Imagine walking through a room where the nearest person to you is 5 miles away, and the next nearest is 5 miles beyond that. That's analogous to the spacing of stars in a galaxy. You're alone in your local space, surrounded by emptiness, with distant companions too far away to affect you directly. This is the nature of the universe on small scales, mostly empty, with occasional dots of matter scattered through the void. And yet, from a distance, galaxies look solid, dense, bright. It's a trick of perspective and light. We see the combined glow of 1 trillion stars, and it looks like a continuous structure. But zoom in, move among the stars themselves, and the emptiness becomes apparent. It's like looking at a distant city at night. From far away, it's a blob of light, but up close, it's mostly empty space with buildings scattered here and there. The universe operates at scales that defy our intuition, where dense still means mostly empty, where galaxies are both solid and gossamer, depending on your point of view. Andromeda's rate of rotation varies with distance from the center. This is called a rotation curve, a plot of orbital velocity versus distance. In a simple system, like planets orbiting the Sun, you'd expect objects farther out to move more slowly, following Kepler's laws. But galaxies don't behave this way. Instead, the rotation curve stays relatively flat far out into the disk, meaning stars in the outer regions are moving faster than they should be given the visible mass. This flat rotation curve is one of the key pieces of evidence for dark matter. Without additional invisible mass providing extra gravity, those outer stars should be moving slowly, or they should be flying off into intergalactic space. The fact that they're not means there's more mass there than we can see. The dark matter halo extends far beyond the visible disk, its gravity holding the outer stars in orbit, explaining the flat rotation curve. Every spiral galaxy shows this same pattern. The rotation curves stay flat far beyond the visible edge of the galaxy, a universal signature of dark matter's presence. It's one of the most compelling pieces of evidence we have for dark matter's existence, observed in galaxy after galaxy after galaxy. Whatever dark matter is made of, it's there, exerting gravitational force, keeping galaxies together. Understanding rotation curves was crucial for the discovery of dark matter. In the 1970s, when Vera Rubin and others measured the rotation of spiral galaxies and found these flat curves, It was a puzzle. The data didn't match the theory. Either our understanding of gravity was wrong, or there was mass we couldn't see. Most physicists believe it's the latter, that dark matter exists and makes up most of the mass in the universe. But alternative theories persist, modifications of gravity that attempt to explain the observations without invoking dark matter. The debate continues, the mystery unsolved. For now, as you rest, know that galaxies are held together by forces we don't fully understand, by matter we can't detect directly. The universe is stranger and more mysterious than it appears, and that's part of its magic. There are nova explosions happening in Andromeda right now. Novae are different from supernovae. They're less energetic, less destructive, but still dramatic events. A nova occurs in a binary star system where a white dwarf is pulling material from a companion star. Gas from the companion accumulates on the white dwarf's surface, building up pressure and temperature until it suddenly ignites in a thermonuclear runaway, a brief but intense explosion that brightens the system by tens of thousands of times for a few days or weeks before fading. These novae are common in large galaxies like Andromeda. Estimates suggest that dozens of novae occur in Andromeda each year, though most are too faint for us to detect. Astronomers who monitor the galaxy with automated telescopes occasionally spot these transient events, watch them brighten and fade, study their spectra to understand the explosion and the binary system that created it. Unlike supernovae, which destroy the star, novae are survivable. The white dwarf remains intact. The companion star keeps feeding it material, and eventually, after enough gas accumulates again, another nova can occur. Some systems are recurrent novae, flashing repeatedly over years or decades. Others nova only once before the system evolves into something else. These explosions enrich the interstellar medium with processed material, elements created in the brief nuclear burning that powers the nova. They also create beautiful expanding shells of gas, though these are too small and distant to see from Earth. Each nova is a small story of stellar evolution, a moment of violence in the long, slow life of a binary system. And they're happening right now, as you listen to these words, as you breathe and relax and drift. The universe is active, dynamic, constantly changing even when it appears static and eternal. Andromeda will eventually merge with the Milky Way to form a giant elliptical galaxy. Elliptical galaxies are different from spirals. They're roughly football-shaped, lacking the flat disk and spiral arms of their younger cousins. They're composed mostly of old red stars, with very little gas or dust, and little ongoing star formation. They're the retirement homes of the galactic world, places where the excitement is over and things have settled into a stable, quiet configuration. The merger will destroy both spiral structures, scrambling the orderly orbits of stars in the disks, puffing up the galaxies into a more three-dimensional distribution. The final product will be larger than either progenitor, containing all the stars from both galaxies, but it will look very different. The beautiful spiral arms will be gone, replaced by a smooth, featureless distribution of stars. It will still be beautiful, just in a different way, elegant, simple, serene. This transformation from spiral to elliptical is common in the universe. When large galaxies merge, they typically produce ellipticals. The process uses up the gas for star formation, either by triggering a starburst that consumes the available fuel or by heating the gas until it's too hot to collapse into new stars. After the merger, the galaxy is left with its existing stellar population and not much else, gradually aging as its stars evolve and die without being replaced. In the far future, billions of years after the Milky Way and Andromeda merge, Andromeda will be a quiet, reddish elliptical, orbiting with the other galaxies in the local group that haven't merged or drifted away. It will be a monument to the collision, a structure that will persist for trillions of years, slowly cooling and fading as its stars die one by one. Eventually, in the unimaginably distant future, it will be a dark galaxy, full of stellar remnants and black holes, no longer shining, just a gravitational well in an otherwise empty universe. But that's so far away it's not worth worrying about. For now, both galaxies are young and vibrant, full of light and activity, beautiful spiral structures turning in the darkness. Enjoy them while they last. Enjoy this moment, this present, this night as you drift toward dreams. Hydrogen clouds in Andromeda glow faintly from stellar radiation. These HI regions, as they're called, are nebulae where hydrogen gas has been ionized by ultraviolet light from nearby hot stars. The ionized hydrogen recombines and emits a characteristic red glow, creating these beautiful luminous regions scattered throughout the galaxy's spiral arms. Earth-based telescopes can detect these HI regions through filters that isolate the specific wavelength of light emitted by ionized hydrogen. They appear as bright knots along the spiral arms, marking regions of recent star formation. Each HI region is a stellar nursery, a place where massive stars have recently formed and are now illuminating the gas cloud from which they emerged. Some of these HI regions are enormous, hundreds or thousands of light years across, dwarfing anything in the Milky Way. The largest HI regions in Andromeda are visible even from our distant vantage point, bright enough to stand out against the galactic background. They're powered by clusters of young, hot stars, dozens or hundreds of them working together to ionize the surrounding gas. Eventually, the stellar winds and radiation from these stars will disperse the gas cloud, and the HI region will fade. The open cluster of stars will remain, drifting through the galaxy, gradually spreading out as individual stars move on different orbits. But for now, these regions glow, beacons of star formation, marking the places where the galaxy is still actively creating new suns. Watching HI regions over time reveals the dynamic nature of galaxies. They brighten as new stars form, fade as gas disperses, move along the spiral arms as density waves trigger sequential star formation. The galaxy isn't static, it's alive, constantly changing, constantly creating. And from our perspective, we see this process frozen in time, a snapshot of activity that's been ongoing for billions of years and will continue for billions more. The metallicity of stars in Andromeda varies with location. Metallicity, in astronomical terms, refers to the abundance of elements heavier than hydrogen and helium. High metallicity stars are enriched with these heavy elements, while low metallicity stars contain mostly hydrogen and helium. Metallicity tells the story of stellar generations, of how many times material has been cycled through stars, enriched by supernova explosions, and incorporated into new stellar generations. Stars in the central bulge of Andromeda tend to have higher metallicity than stars in the outer disk. This is because the bulge formed earlier from denser gas that underwent more rapid star formation, quickly enriching itself through multiple generations of massive stars exploding as supernova. The outer disk formed more slowly from less dense gas, with fewer generations of enrichment. The halo stars have the lowest metallicity, characteristic of the oldest stellar populations. These stars formed early in the galaxy's history, before significant enrichment had occurred. Their metal core, composed almost entirely of hydrogen and helium, with just traces of heavier elements. Studying these stars gives astronomers a window into the early universe, into the conditions that existed when the first galaxies were forming. Metallicity affects stellar properties. Higher metallicity stars have different colors, temperatures, and evolutionary tracks than low metallicity stars of the same mass. Metallicity also affects the likelihood of planet formation. Heavy elements are needed to build rocky planets like Earth, so low metallicity stars are less likely to have planetary systems. Our Sun is a relatively high metallicity star, enriched by previous generations, containing enough heavy elements to form the planets, asteroids, and comets of our solar system, and ultimately, enough to form us. Every atom of carbon in your body, every atom of oxygen you breathe, was created in a star and dispersed by a supernova or stellar wind. You're made of stardust, as Carl Sagan famously said, and that stardust's abundance increased over cosmic time as more and more stars enriched the interstellar medium. We're late-generation, high-metallicity beings built from materials that didn't exist in the early universe. And that's part of our story, part of what makes us possible. Andromeda's brightest globular cluster is called Mayol 2, also known as G1. It's visible in large amateur telescopes as a faint point of light near the galaxy, and it's actually one of the brightest and most massive globular clusters known in the local group of galaxies. G1 contains several million stars in a region only about 200 light-years across, making it incredibly dense at its core. This cluster is so bright and massive that some astronomers wonder if it might actually be the stripped core of a dwarf galaxy that was cannibalized by Andromeda long ago. If so, it would be the leftover heart of a galaxy that no longer exists, all its outer stars torn away by tidal forces, leaving only the densest central region. This is speculation, but it's plausible. Galaxies do consume their satellites, and sometimes remnants persist. Globular clusters are laboratories for stellar dynamics. With so many stars in such a small volume, gravitational interactions are common. Stars can be ejected from the cluster by close encounters, flung into the galactic halo. Binary stars can form from chance encounters. Exotic objects like blue stragglers, stars that appear younger than they should be, form through stellar collisions or mass transfer in binary systems. G1 has been studied extensively because it's bright enough to resolve individual stars with large telescopes. Astronomers have measured its age, metallicity, stellar populations, and dynamics. It's ancient, about as old as the universe, and it's been orbiting Andromeda for billions of years, a satellite within a satellite, a tiny city of stars bound together by gravity in the outer reaches of a vast galaxy. When you look at images of Andromeda, G1 is sometimes visible as a small bright, slightly separated from the main galactic structure. It's easy to overlook, just another point of light, but it contains millions of stars, millions of suns, each with its own nuclear furnace, its own life story. The universe is like that, full of things that seem small but are actually vast, full of details that reward closer inspection. The Andromeda Galaxy is approaching us at about 300 kilometers per second when you account for both its motion and the Milky Way's motion. Earlier, I mentioned 110 kilometers per second, which is Andromeda's velocity toward us. But the Milky Way is also moving toward Andromeda at about 190 kilometers per second. When you add these together, accounting for the relative motion, the closing speed is about 300 kilometers per second, or roughly 670,000 miles per hour. That's fast by any human standard, but on cosmic scales, it's a gentle approach. It will take 4 billion years for the galaxies to meet, plenty of time for stars to complete millions of orbits, for stellar generations to turn over multiple times, for planetary systems to evolve and die. The collision is inevitable but not imminent, written in the equations of gravity and motion, but still unimaginably far in the future. During the merger, which will take several 100 million years from first contact to final settling, the galaxies will pass through each other multiple times, their gravity tugging and pulling, gradually slowing their relative motion and causing them to fall back together. Each passage will be dramatic from a galactic perspective, reshaping both structures, but from the perspective of individual stars, it will be slow and mostly uneventful. Eventually, the two galaxies will lose enough energy to their gravitational interaction that they can no longer separate. They'll spiral together, merge, their central black holes eventually meeting and merging as well in a gravitational wave event that will ripple across the universe. The stars will settle into new orbits around the common center, and the merged galaxy will begin its long existence as an elliptical, a monument to the union of two great spirals. All of this is predicted by physics, simulated in computers, understood in principle even if the details are complex. The future is knowable, at least in broad strokes, because the laws of nature are consistent and reliable. And that's comforting in a way. The universe follows rules. It's not capricious or random. Given enough information and computational power, we can predict what will happen billions of years from now. We can see the future written in the present, in the positions and velocities of galaxies, in the inexorable pull of gravity. And yet, despite knowing the outcome, despite being able to simulate the merger and watch it unfold and fast forward, there's still mystery. There's still beauty in the unknown. We don't know what it will look like from Earth. Don't know if Earth will still exist. Don't know if anyone will be here to witness it. We don't know the small-scale details, the individual stories, the particular path our solar system will take through the chaos. The broad strokes are predictable, but life is lived in the details, and those remain mysterious, uncertain, open. Rest easy knowing that the universe is both knowable and unknowable, both predictable and surprising. Rest easy knowing that some questions have answers and others don't, and that's okay. Rest easy as Andromeda approaches through the darkness, patient and inevitable, a future we can imagine but will never see. There are X-ray binaries in Andromeda, systems where a compact object, a neutron star or black hole, is pulling material from a companion star. As this material spirals into the compact object, it heats to millions of degrees and emits X-rays, creating some of the brightest X-ray sources in the galaxy. These systems are violent, energetic, dramatic, yet they're also stable, having persisted for millions of years in this configuration. The X-rays from these binaries are invisible to optical telescopes, but bright to X-ray observatories like Chandra and XMM Newton. Astronomers have cataloged hundreds of X-ray sources in Andromeda, each one a story of stellar evolution taken to an extreme. Some are systems where a neutron star, the crushed core of a dead star, feeds on its companion. Others contain stellar mass black holes, objects so dense that not even light can escape their gravity. These systems will eventually run out of material to accrete, or the companion star will evolve and die, ending the X-ray phase. Some will become isolated neutron stars or black holes, dark and silent, drifting through the galaxy. Others might have dramatic endings, nova explosions or supernovae, brief fireworks before settling into whatever comes next. For now, they shine in X-rays, beacons of extreme physics, laboratories where gravity and matter and energy interact in ways that push the limits of our understanding. You don't need to understand the physics of X-ray binaries to appreciate their existence. You can just know that they're out there, in Andromeda and in our own galaxy. Exotic objects doing exotic things, contributing to the rich tapestry of phenomena that make galaxies complex and interesting. The universe is full of variety, full of different ways for matter and energy to arrange themselves. And that's beautiful. Andromeda contains regions of shocked gas where supernova remnants expand into the interstellar medium. When a massive star explodes as a supernova, it sends a shock wave racing outward at thousands of kilometers per second. This shock wave compresses and heats the gas it encounters, creating a glowing shell that expands for thousands of years before finally fading and merging with the ambient medium. These supernova remnants are visible in certain wavelengths, glowing in optical light from ionized hydrogen, in X-rays from superheated gas, in radio waves from accelerated particles. There are circular or irregular shells, expanding bubbles marking the sites of stellar death. Each one is the remnant of a star that lived for millions of years and died in seconds, releasing more energy in that brief explosion than our sun will emit in its entire 10 billion year lifetime. The shock waves from supernovae compress nearby gas clouds, sometimes triggering new star formation. So death leads to birth, destruction leads to creation, the cycle continuing endlessly. The heavy elements forged in the star's core and in the explosion itself, carbon, oxygen, iron, all the elements necessary for planets and life, are scattered into the interstellar medium, enriching it, making future generations of stars and planets more complex, more interesting. Our own solar system formed from a cloud enriched by previous supernovae. The iron in your blood, the calcium in your bones, the oxygen you breathe, all were created in stars that exploded billions of years ago before the sun existed. You're made from the remnants of ancient supernovae, recycled stellar material given form and consciousness. And in Andromeda, the same process continues, stars exploding, elements scattering, future generations being seeded with the building blocks of complexity. It's all connected. The life cycle of stars, the enrichment of galaxies, the formation of planets, the emergence of life. Each step depends on what came before, and each enables what comes after. The universe is not just a collection of objects, but a web of relationships, pauses and effects spanning billions of years and millions of light years. And you're part of that web, a node in the network, connected to everything through the atoms you're made of and the light you see. Dust lanes in Andromeda trace the spiral arms, dark bands where interstellar dust blocks the light of background stars. Dust might seem like an imperfection, an obstruction, but it's actually vital. Dust grains are where complex chemistry happens, where atoms meet and bond to form molecules. Dust is where hydrogen molecules form, and those molecules are necessary for star formation. Dust shields the interiors of molecular clouds from destructive radiation, allowing them to cool and collapse. Dust is also where organic molecules form, the building blocks of life, created in the cold darkness between the stars. The dust in Andromeda is made of tiny particles, smaller than the width of a human hair, composed of carbon, silicon, oxygen, and other elements. These grains condense in the atmospheres of dying stars, in the ejecta from supernovae, then drift through space, accumulating in the spiral arms where they trace out the densest regions of gas. When stars form from molecular clouds, planets form from the dust that accompanies them, solid objects coalescing from tiny grains that stick together through electrostatic forces and gentle collisions. Without dust, galaxies would look different, brighter, more transparent, but also less capable of forming stars. Dust is essential to the process of creating new stellar generations. It's a reminder that even things that seem like obstacles or imperfections often serve important functions, vital roles. The universe is efficient, using everything, wasting nothing. What seems like debris is actually raw material. What looks like obstruction is actually necessary infrastructure. Looking at Andromeda's dust lanes, you're seeing the scaffolding of star formation, the dark regions where future stars are gestating, waiting to be born. In 1,000,000 years, some of those dark lanes will be bright with new stars, the dust dispersed by stellar winds and radiation, the molecular clouds transformed into open clusters. The galaxy is constantly renewing itself, constantly creating, constantly transforming darkness into light. We've traveled far tonight, you and I, 2.5 million light years across space and billions of years through time. We've visited the spiral arms where stars are born, the ancient halo where the oldest stars drift, the warped disk shaped by gravity, the dark matter that holds everything together. We've thought about black holes and blue stars, tidal streams and planetary nebulae, globular clusters and supernova remnants. We've imagined a future merger, a cosmic collision that will reshape both galaxies into something new. Andromeda is there right now, in the night sky, whether you're looking at it or not. 1 trillion stars turning in the darkness, 2.5 million light years away, approaching us at 300 kilometers per second, patient and inevitable. It's been there every night of your life, and every night of every human life that came before you. Ancient people saw it without knowing what it was. Medieval astronomers cataloged it without understanding its distance. Modern scientists study it, measure it, simulate its future merger with our galaxy. And still, it keeps its mysteries, its secrets, its sense of wonder intact. If your eyes are heavy now, that's just fine. Let them close. Let the images of spiral arms and ancient stars drift through your mind as you settle into sleep. Let the vast scales, the trillions of miles, the billions of years, the incomprehensible numbers, become a soft blanket of perspective, reminding you that your worries are small and manageable against such a backdrop. The universe is large, but you're part of it, made from its atoms, illuminated by its stars, conscious of its beauty. Tomorrow, if you remember any of this, perhaps you'll look up and think of Andromeda. Perhaps you'll feel a little more connected to the cosmos, a little more aware of the deep time and vast space that surround our small lives. Or perhaps you'll simply sleep well and wake refreshed, and that's enough. That's all this was for, a gentle journey to ease you into rest. Thank you for spending this time with me, for listening to these stories about our galactic neighbor. Thank you for your curiosity, your willingness to wonder, your trust in letting these words accompany you towards sleep. I hope you sleep well and dream softly. May your rest be deep and your morning bright. The music will continue for a while longer to help you relax. Good night.